How can a neutron fall apart in minutes while a proton, built from the same three quarks, can almost live to the end of the universe? In the energy filament theory, the difference is not in what quarks you use, but in how the three tension bridges between them pull on the whole structure, and whether they leave the energy sea feeling relaxed or slightly annoyed. Picture the proton first. 3 tiny quark rings sit in the energy sea, and each one drags along a one-sided straight texture. When they line up just right, those 3 textures connect tip to tip and become 3 clean bridges that lock the rings together and pull the outer side of the composite ring tight while leaving the inside a little looser. To the energy sea, this looks like a small fortress that is tight outside and softer inside, and that pattern hits a very comfortable rhythm. So the sea is happy to let it sit there for billions of years. That is what we call a positively charged, extremely stable proton. A neutron starts from almost the same ingredients, but with one crucial twist. Of the 3 bridges, one has its pulling direction flipped. Instead of all 3 pulling outward in a balanced way, 2 bridges still support the outer tension while the third begins to cinch inward. The structure does not collapse instantly, but the load is now uneven. In everyday terms, the proton is a tent with 3 ropes all pulling outward, keeping the fabric smooth and firm, while the neutron is the same tent with 1 rope ray tied so it pulls back toward the center. The tent still stands, yet it leans slightly. One side feels tight and wrong, and you can tell the system is using extra effort just to avoid falling over. Translated back into the energy sea, the neutron's tight-loose distribution is no longer as clean as the proton's. The outside is not as tight, the inside is not as relaxed, and the pattern is stuck in a narrow, almost stable window, not loose enough to instantly fall apart, not comfortable enough to be truly permanent. It is like a dancer holding a twisted posture. They can stand like that for a while, but their muscles are secretly burning, and sooner or later they will shift into a more natural stance. Now remember that the energy sea is never perfectly calm. It is always trembling, sending tiny ripples and background waves through every structure inside it. Each little nudge pushes on the neutron's awkward pattern and gives it a chance to leak a bit of extra tension into the surroundings. Every time a bit of that wrong tightness leaks out as fine disturbances in the sea, the neutron's internal tight-loose map slides a tiny step towards the proton's ideal pattern, almost as if invisible fingers were slowly readjusting that flipped bridge to better match the other 2. This is not a clean, single jump at first. It is a gradual drift. But once those tiny adjustments accumulate to a critical point, a threshold is crossed. At that moment, the structure no longer just makes small corrections. It seizes the chance to perform a full rearrangement into the cheaper, smoother proton configuration. In that rapid reconfiguration, 2 things happened at once. First, the 3 bridges switch into the proton-style pattern where all of them cooperate to pull the outside is tight and allows the interior to sit more relaxed. So the composite object suddenly drops into a much more stable energy minimum and effectively becomes a proton. Second, the tension surplus and extra filament material released in the rearrangement cannot simply vanish. The sea rolls them up into a new pair of small structures, an electron and an antineutrino, which carry away the leftover energy and the leftover texture that no longer fits inside the new proton. From far away, we summarize this neat, microscopic reshuffle with a simple equation. A neutron decays into a proton, an electron and an antineutrino. From up close, in this filament picture, it is just a slightly awkward 3-bridge fortress finally. From up close, in this filament picture, it is just a slightly awkward 3-bridge fortress finally choosing the more economical design and packaging the remaining awkwardness into moving wave packets and new particles that leave the scene. This also explains why free neutrons always share the same fate. As long as a neutron is alone in the sea, not locked inside a nucleus where other particles help share and redistribute tension, it will be nudged again and again towards the lower-cost proton pattern, until the full rearrangement becomes inevitable. In that sense, every neutron carries a built-in direction of travel written into its geometry. When it is left on its own, Its natural home state is becoming a proton and shedding the excess. Tap follow, share it on New Physics, Clear Universe.